chamber, when everything's tuned properly, is turning whatever we use as a fuel into a plasma. What is a plasma? Plasma is a state of matter. Now, in matter we have solids, we have liquids, we have vapors like the water that's in the air now we call humidity, and then a step above that would be plasma. Well, what's the difference between a vapor and a plasma? That was a question I had for a long time. Let's look at water as the example. In the solid form we have H2O, ice. In the liquid form we have H2O, water. In the vapor form we have H2O, humidity. In the plasma form we have H plus O, plasma, free-floating atoms. Not oversimplifying it. I mean, there's ionic charges and things that I'm all confused about myself. But what we've done is we've taken a stable molecule and we've let the atoms free float. We no longer have molecules, we have free-floating atoms. Essentially, that's what we're trying to do to our fuel in here. Now, what does it take to create plasma? Well, it takes a lot. There's no lie about that. It takes a lot to turn matter into plasma. In fact, if we look at water, to turn water into plasma state requires about 3,800 degrees Fahrenheit at atmospheric pressure. But if we were to put that same water in a vacuum, 720 degrees Fahrenheit would give us our plasma. So under a vacuum, we can lower the energy requirements. But now, wait a minute. First of all, we're not getting a perfect vacuum here. We're only getting, 8, 10 inches of vacuum under normal operating conditions. That's not enough. And we're not getting 3,800 degrees here or even near enough heat to turn our fuel into a plasma, even with the vacuum. But wait a minute. We have hot and cold going in opposite directions, don't we? That creates an electromagnetic field, right? Like a nice warm day like today, a low-pressure cold front moves in, the hot and cold collide, and what do you get? You get energy buildup. Electrons excited. And after a while, that energy will discharge in the form of lightning. So, hey, okay, we got that. And to illustrate how an electromagnetic field can affect the bonds that we're trying to break, think of a permanent magnet. 1 inch diameter, 6 inches long permanent magnet, and then a chunk of steel of the same dimensions. We get the two of those close together, and they lock jaws. Kind of like an atom and a molecule. Now, if we take that piece of steel and we wrap some wire around that and hook it up to a battery, we might have to flip the battery once, but we can get a north-to-north polarity. And when that happens, the two chunks of metal will repel each other, right? The speed of sound has this ability of very much destabilizing structure. Now, here's a little law of nature. There's a Venturian here. That's what you get when you have that reaction rod inside the pipe. It's a restriction. It's a Venturi. And the old carburetors, a lot of them would have a port in the Venturi, so you would have Venturi vacuum. Well, if you put a gauge on that port, measure that Venturi vacuum, and rev the engine high enough, and you would actually get 11 to 11.5 inches of Venturi vacuum. The air going through that carburetor would be traveling at the speed of sound, Mach 1. 11 to 11.5 inches of Venturi vacuum. So with this system, if we can get our air-fuel charge up to 11 to 11.5 inches of Venturi vacuum here, that doesn't mean the vacuum at the outlet side, the Venturi vacuum. Now we've got one more destabilizing factor. We've got the speed of sound. Plus thermal inertia. I've explained this before. It's like if you're getting on the freeway, you put the pedal to the metal because here comes a big old Schneider truck you want to beat. You get out on the freeway and you look down, up we're doing 75, and you back off. That speedometer will continue to climb for a little bit and then start to drop back down, right? Inertia. Let's go back to the reactor. We've got this relatively cool fuel vapor coming up in here. We'll say 110, 120 degrees. We've got this hot exhaust coming down through here, and at this point it's about 1,000 degrees. Hot and cold going in opposite directions. Now in nature, hot and cold actually physically collide. But here we have a pipe inside of a pipe. But the effect's the same. It's just like wearing gloves. You got surgical gloves on, you can feel what you're doing. You get the job done. The fuel is exposed to hotter and hotter and hotter walls as it travels up through. The exhaust is exposed to colder and colder and colder walls as it travels down through. You still get the same effect. Meanwhile, the fuel comes in here at a pretty slow clip, and it hits that rod, takes off. We're up to the speed of sound in no time. Remember inertia? Plus the rod's pushing that fuel out against those hotter and hotter walls. Temperature takes off. Thermal inertia. We actually have a point right about here in the middle where the fuel temperature exceeds that of the exhaust so much that it starts raising the temperature of the exhaust again. So we come out of here 1,000 degrees. Here we are about 880 degrees. Drop down about 450 degrees somewhere in here. And then from 450 degrees, it'll spike back up to about 700 degrees. And then from there, it'll linearly drop off again. So the temperature of the exhaust comes out of here, starts dropping off, spikes up, and then starts dropping off again because of the thermal inertia factor. Now, we take thermal inertia. We're getting a lot more heat energy, thermal energy, into the fuel than what we, per se, have in the exhaust here. But not enough to disassociate matter into plasma. But we're doing it under a vacuum. That's still not quite enough to turn our fuel into a plasma. Hey, but we've got the electromagnetic field that's bouncing around here. You see, all of these elements combined together as a team. No one man can do it by himself. You ever hear that? You got to work together as a team. We've got a team player here. Common stuff. Any science book, high school, college, it's all in there. It's just nobody ever tried putting them all together like this before. If you run the fuel and the exhaust in the same direction, you don't get a reaction. Take the reaction rod out, you don't get a reaction. So that's how the reaction chamber works. That was the second subassembly. Now we go to the third subassembly, the air management valve. The air management valve on this engine is two-part. Our air valve here and our fuel valve here. And on an automobile or the generator, we can fit it all together into one compact unit where we have a fuel valve here and an air valve here. The air management valve can be on a stationary speed engine, like the generators, just one valve. On the generator, we took the stock carburetor that mounted here. We have the choke plate that we turn on to start it. Once we get it started, you slowly have to turn that choke off. As the heat builds up and we start getting warmer and warmer, you can slowly turn that choke off until you finally get a reaction going, then you can turn it off altogether. Meanwhile, the governor is working that little throttle plate over here as you change the load on it to maintain that constant speed. And this doesn't work on automobiles. I tried it. Take it one step further. The generators. If you run the stock generator, we use 8-ounce cups for our testing. I mean, they have 7-gallon tanks on them. It would take forever to do any kind of testing. So we just 8-ounce cups at a time. We do our timing, watch the emissions. The stock generator would run about 4 minutes and 45 seconds on 8 ounces of gasoline at half load, which is an industry test standard, half load. We put the GEET fuel processor on there, and we've gotten it as high as over 10 minutes on 8 ounces of gas, half load. But then we do a 50% gasoline, 50% diesel mix in there, 8 ounces, 4 ounces of each for a total of 8 ounces, half load, and now we're up to over 14 minutes. So as you add higher energy fuel to the GEET, you get higher energy out. So if you put propane in, you get something a little bit smaller out, but the efficiency increase isn't there. Put crude oil in there, crude oil, used engine oil, something that's really got a lot of energy in it, and shove that up in there. Paul's blue engine, the one that's set up kind of like this with the aluminum bubbler here, big long board, that's set up to run on crude oil. And on 8 ounces of crude oil, that son of a gun will run practically for a day, day and a half. Lots of energy in it. So, to answer your question, I would much rather use gasoline than propane because there's a lot more energy in the gasoline. The cost per hour of operation is much less on the gasoline than the propane.